welcome back, everyone. So today we're going to make a little prerequisite video to a follow-up video we're going to do, which is a video about the Bolzano-Weierstrass theorem, a very well-known theorem in real analysis. So we have to cover it, of course, and that is going to be a tool in order to prove that Cauchy sequences are or a sequence is Cauchy if and only if it's convergent. So that's going to be a big result we're going to prove after that. Then perhaps we'll get into compact sets, just jump to that, because why not, right? So that's kind of our progression, an outline of it, anyway. So let's just take a look at this theorem. So if we consider non-empty nested closed sets, A1, B1 contained in, or I should say, it's kind of difficult to word this, but A2, B2 is contained in A1, B1, A3, B3 is contained in A2, B2, etc. Okay? And then we want to show that this infinite intersection of all of these nested closed intervals is non-empty. Okay? And actually we're going to kind of use a kind of special case of the nested interval property to prove the Bolzano-Weierstrass theorem, Weierstrass, if you will. And that's that, well, there's actually a special case where not only is this intersection non-empty, but it only contains a single element, and that's going to be the supremum of a certain set we're about to look at. And that occurs when the distances between an and bn, so these endpoints, shrink to 0 as n tends to infinity. Okay, so kind of as these, because notice that this inclusion doesn't necessarily imply that this isn't a proper subset, not necessarily, right? This A1, B1 could be equal to A2, B2. So this is a stronger or more general case of what we're going to use, but it'll be useful nonetheless. So let's kind of take a look at this useful picture. So we have this A1, B1, A2, B2 is contained in that, A3, B3 is contained in A2, B2. Sounds like R2D2. Huh. Anyway, it keeps going on like that. Again, I didn't make it so that one of these sets was equal to another because that's kind of hard to draw, but you get the idea. And we want to show that, and again, we want to show that intersection is non-empty. Okay, so how do we go about that? Well, we kind of want to find an element that's in all of those, that's in all of these, we want to find a candidate that's in all of these, that could be in this intersection, meaning it's in all of these sets. So for all natural numbers k, this number that we want to find is inside a k to bk. Okay, so let's perhaps find such a candidate. And to do that, let's consider the following sequence. Consider the sequence given by a sub n. So all of these left endpoints, that sequence. Okay. So, well, what can we get from the sequence? Well, first of all, if we take, let's take an arbitrary endpoint, A3, well, this A4, B4 is contained in A3, B3, so by definition, it must hold that, well, A4 is greater than or equal to A3, so then that will hold for all n, so then for all n, maybe I should say for all k in the natural numbers to differentiate notation, a sub k is less than or equal to a sub k. Meaning it's an increasing, this sequence is increasing. So a sub n is increasing. Right? That's going to be key. So that means it's monotonically increasing, okay? Furthermore, what else do we know? So get ready, we're going to be using the monotone convergence theorem in a second. Well, also it's bounded, right? It's bounded, for example, by B1. That's a bound, right? B2 is a bound, B3 is a bound. All the B's are bounds, okay? And that's by construction, right? So furthermore, A sub n is bounded. Obviously the trivial bound, the easiest bound to see, the first bound you might see is B1. So by B1, for example. Okay, but what does this tell us? I should say bounded from above, although it is bounded because it's bounded from below by A1. Anyway, what does this tell us? Since it's increasing and bounded from above, then, well, by the monotone convergence theorem, so I'll write it MCT, this A sub n converges. A sub n converges to something let's call S for kind of supremum, because when you prove the monotone convergence theorem, along with that, you construct the limit of your sequence that's monotone. In this case, monotonically increasing, so it's the supremum. If it's monotonically decreasing, then we're going to have the infimum, right? So S is the supremum of this sequence, which can be written as a set, right? Perhaps that would be better to write, but it's fine. So S, this is, alright, S equals the sup of A sub n, like that. Okay? Okay, well, how does that help us? Now we have an actual candidate for something that could be in this intersection. Intuitively, it should be in that intersection, right? But we have to kind of prove that. Obviously, we're proving this rigorously. We're in a real analysis class. So, well, how do we do that? Again, we show that, well, for all k in the natural numbers, this S is inside A sub k to B sub k. Then take an arbitrary k in the natural numbers. Notice the following. Well, okay, A sub k is surely in the set A1, A2, all the, that runs through all the natural numbers, okay? And then, but S is taken to be the supremum of that set. Namely, if we take any element in that set, S is surely an upper bound for that set, so it's always greater than or equal to any element in that set. Notice that. So that means if we just take A sub k in particular, S is greater than or equal to S. S is greater than or equal to A sub k. Okay, so, well, that's the first condition we need to be in this closed set. And, well, as we stated before, hinted at, all of these B's are upper bounds for these A's. Namely, since they're all upper bounds, well, surely B sub k is an upper bound for all our A's. So that means, well, since S is the supremum, by definition, given any upper bound, the supremum, given any upper bound of a set, the supremum of that set is always less than or equal to that upper bound. Well, it's the at least upper bound, right? It's in the name. And S is less than or equal to B sub k. This is an upper bound, just to make that clear, of A sub n. Okay? So that just means S is inside this closed interval A sub k to B sub k for all k. So that just completes the proof. We found at least one element that's inside this intersection. One can show that this doesn't hold for all open sets. I'll maybe leave that as an exercise, maybe as a hint. Consider something like 0. Consider something like this. I believe that should work as a counterexample to this. This should be, this intersection should be empty. You can show that using the Archimedean property. I'll leave that as an exercise. So again, in the next video, we'll be proving the Bolzano-Weierstrass theorem. So see you then, QED.